In this project, we used a bottle with a diameter of approximately 8 cm, volume of 800 milliliter, and a hole at its side that has a diameter of 0.8 cm. We filled the bottle and let it drain out, and repeated this experiment for different initial heights. For this experiment, we used the Bernoulli model to get the velocity of the water. Now, by considering the relationship between velocity and flow rate, and then taking the mass balance, we can derive expressions for the height and velocity of the water. We observed disparities in the time to drain the water out of the bottle. The disparity between the theoretical time to drain and the experimental time to drain can be explained by the limitations of our model. The Bernoulli equation assumes that the effects of viscosity are negligible. However, as the hole in a bottle becomes smaller, the effects of viscosity are too large to ignore. No, since the hole in our bottle is quite small, the effects of viscosity are not completely negligible, and that reflects in our experimental data. To make our design better, we could have made a larger hole in the bottle. The cross-sectional area of the tank affects how quickly the water level drops as it drains. For a wide tank, the water level decreases more slowly for a given outflow, while for a narrow tank, it decreases more rapidly. Additionally, if the tank's cross-section changes with height, the rate of water level drop will vary as the tank empties. This is because the volume per unit height changes with the cross-sectional area at different levels. The location of the opening would affect the drain time since more liquid would drain the bottom case. From the equation u equals square root of 2gh, we see that velocity depends on the height. If the height were to be lowered, the velocity would thus decrease. The assumption of small opening becomes invalid when the opening is either too large or too small, such that the Bernoulli model makes incorrect assumptions about the behavior of the water.